Good morning, ladies and gentlemen. So we are at the course of advanced quantum mechanics, and there is problem solving session. Let me say a couple of words about the course in general and about presentations. So what I'm going to do today is a presentation. It is taken from the list of student presentations. As you know, everybody who wishes that would do presentation for this course in a team of 5. Today, there will be first round of these presentations for 4 groups, for 20 people. Why do we have these presentations in the course? Well, several reasons. First of all, it's good to present. It's good that students kind of polish and sophisticate their presentation skills, and not just presentations about something which you could Google, but something which concerns science, scientific presentations. Right. Another reason is to give the notion that the course which we learn is not like usual old-fashioned course when you have to learn law number 1, law number 2, law number 3, and up to 7. And then you would be able to cite these laws and everything is okay. Not really. Advanced quantum mechanics is not a science to learn by a sequence of laws. It is rather a tool set, right? So there are some problems which real world formulates for us. And we can get understanding of these problems by certain tool set, by certain set of methods, right? So the presentations, the topics of the presentations are very various, have been taken from different fields, and they don't really compose anything logical. Like the whole world around us is not that very logical, right? Students pick up methods and they basically exercise with this particular set on an example of a problem. Why do I have this long introduction? Because it's what I am going to do today. This presentation can be given by a student, but I don't do it in the manner of student would do it without PowerPoint slides, whatever. It's just about the tool set. What I will do today, I will play with creation, annihilation operators in order to achieve a certain goal, in order to solve a certain, let's call it practical problem. Fine. Sure, I must warn you, it is not obvious to which extent it would be useful for you in your practical problem of passing the course. Yeah, perhaps anything what I will tell you today won't be applied at your examination, right? But okay, we find it important to illustrate you tool sets in these situations. Good. Right. So as usual, all questions, but anything which I say from philosophical considerations till mathematical details, Please put questions to the chat. I will be glad to answer those. Sure. What problem do we have at hand? We talked about superconductivity in previous lecture, and we have solved this problem in some particular method. The method is very similar to what is done in the original paper of Bardeen, Cooper, and Schiffer. Since that, people found it convenient to use a bit different method, which is summarizing, I would call it Bogolyubov-Dejean equations. Right. And this is a bit alternative to what we do, but in fact, it's a very surface-like alternative. It's not fundamentally different. It's different in some mathematical details, mathematical notations. And what we are going to do is to just solve this, is to understand that both methods are equivalent, and understand the advantages of this new method. Here it's explained what this is the advantage. Right. First of all, it will involve a transformation from particles to quasi-particles. We have had it in the lecture, but it won't the backbone of the derivation. Right, and we will introduce an effective Hamiltonian for the superconducting state first, and we will show that it can be brought to the set of independent quasi-particles rather than particles. So in fact, we will run transformation, which is commonly called Bogolyubov transformation, and Dejean has what Dejean did. He kind of sort of make it popular in the context of superconductivity. And we will show that this is useful. We will find the relation between energies of quasi-particles involved and the energy of the ground state of the superconductor. Right, and we go step by step through the problem. Right. At some stage, people like Bardeen, Cooper, Schiffer, they just had this skill set, they applied, they didn't know the answer, right? They just have been playing with the tools, they got some product. In most steps, I will outline, we will use kind of reverse programming, I would say. We will know the answer, and we will show that this answer corresponds to something which we have already learned. Good. So thereby I come to step A. Let's have a little bit of problem with scrolling due to peculiarities of Zoom. Fine. So far, we know what is the energy of superconductor. I will remind you our calculation in a second. We feel we want to show that the same energy one can obtain in a different way. with the help of effective Hamiltonian. So this Hamiltonian is kinetic energy, you know that. And we have an addition to this, rather strange addition. This addition doesn't conserve the number of particles. So it has kind of wrong structure. There are two annihilation operators in a row. There are two creation operators in a row. Okay, these terms are conjugated with respect to each other. Otherwise, the whole Hamiltonian won't be Hermitian. It's okay. We just got new terms, which were not in original Hamiltonian. So the question is how? Right. How do we get it? That's basically the answer given. And we will take delta as a parameter. We will minimize this expression with respect to delta and get the answer for energy. And then we will compare it with what we know. All right. Fine. Let's get to work. So this expression to minimize has the terms. One depends on delta and doesn't depend on any operators. So it's just a function of delta. It's quadratic function. We can easily minimize quadratic function. All right. So what is the minimum? If you take only this term into account, what would be the minimum with respect to delta? Thank you for giving me time to rest, but I kind of like you to remember the simple rule of this course. If I ask something with high probability, the answer is 0. Good, it's 0. Well, because it's just a positive term. I could sketch it as a function of delta. It is something like this. Parabola. And the minimum is here. Fine. Then let me look here. This term has two contributions. Oh, I did something wrong. Just a sec. This term has two contributions. There's a contribution from H1. And that we don't touch because it doesn't depend on delta, right? It doesn't does not play any role in our minimization procedure. And that will, it is actually what it is. It's average kinetic energy of the superconductor. We have evaluated it, we know the answer. In addition to this, there is a term coming from this. So let me rewrite it term by term. I concentrate on this expression. So what I have, delta in front of it, and then sum over k Fine. So this is expectation value with respect to some wave function psi of this combination of the operators. But let me just, in order not to rewrite these C's again and again, let me recall that in the lectures we have had already some notations for this combination of operators. First of all, individual term is a creation of Cooper pair in a state labeled by K. And if we sum it up, we got the definition. Okay, it has to be conjugated creation. We have already we have also defined the sum of these zetas over K, and that was nothing but, let's see, operator delta. So let me use this. Oh, okay, I've forgotten the text. Operator delta. Sure, I could, since I don't want to write all the C's, I will immediately replace the C's with an operator. Again, there's a difference. There's a number, delta, and there's operator, delta. Fine, so let me do this. I have to remove this. And put delta dagger here. That I don't need. Right. Then I need to deal with this term, but it's kind of rather trivial because it just conjugated of the term, complex conjugation of the term which I have written earlier. So that would be delta conjugated. And I want to take expectation value of the conjugated operator. Good. Then let me put this term. This positive term. So now I'm going to minimize, right? Minimize, I have to take the minimum with respect to delta. Okay, delta is complex number. It has real and imaginary parts. Therefore, I can minimize over complex delta, since delta conjugated, I can minimize with respect to one complex number only. So I have delta and delta conjugated, but they're also related. So I need to minimize with respect to only one number. So what do I have to do? Well, I would like to find a minimum of this energy So I differentiate what I have with respect to delta. Okay, this term gives me all right, this is clear. So just differentiate. I have removed the separator. And let us see. This doesn't contribute, it depends on delta conjugated only. All right, that is delta times delta conjugated. So I rewrite it as fine. So now I can solve it. Let us see. Minus. I got a bit tired to write this psi function all the time. So let me just write it as expectation value. Good. I have found the position of the minimum. I have not yet found the minimum itself. How do I do this? Well, I just substitute. This delta to here and here. Let us see what do I have from the first term. Right, minus u divided by v and minus u. So these two terms just contribute equally and with minus sign. Let us see now. I need to substitute it here. It is squared. So I have plus. I'm working the third term. I sum them up. All right, so these terms cancel each other. That's my answer for the energy. And okay, I redefine operator delta here in comparison with what we have in the lecture. If I take these notations into account, yeah, I will get just the potential energy which we have evaluated. That's how I reproduce the answer. Let's see. we have covered this point. We understood that instead of evaluating separately potential and kinetic energy, we sorry, we can use this effective Hamiltonian. We can use the expectation value of this effective Hamiltonian. Let us see there are questions. Why you can replace the complex conjugated delta by just delta. This is not what I did. What I did here is to consider delta and delta conjugated as independent variables. Right? So I differentiate and found the minimum only with respect to this delta without touching conjugated one. Modulus delta, Sasha. As you remember, is a product of delta and delta conjugated. So again, when I differentiate only with respect to this delta, not touching this one. Alternatively, I could differentiate with respect to variables, imaginary part, with respect to two real variables, imaginary part of delta and real part of delta. But what I did is just faster. This is equivalent, but faster. Right, after differentiation, I expressed delta conjugated. I have found expression of delta conjugated. Yeah, that's what we got. It is 0, right? We find the minimum that has to be 0. But okay, delta equals to delta conjugated. I just need to conjugate this expression. That's what I did. So this operator got also conjugated. All right, is it clear now? Fine, good. So and now we want to work with this operator, effective superconducting Hamiltonian HS. And let me go to next page. That will be next point. Right. How's question? How's the expectation value of that k is not 0 when the creation operators are not balanced by annihilation operators? That's precisely the point. That's precisely the point. It's a simple point, but let me reiterate it again. Operator Z, it just made from these operators. And if in the Hamiltonian, each operator, each annihilation operator is compensated by a creation operator that has all chances to be 0. In other terms, eigenvalues, eigenstates of a Hamiltonian where all C's come with C conjugated come with C, eigenvalues of this Hamiltonian are not superconducting. But if one considers this Hamiltonian, here's the symmetry, the fact that all C conjugated comes with C is broken. Yep, remember what I said about broken symmetry? Right. So in this Hamiltonian, we do expect non-zero expectation values like this, even for eigenstates of the Hamiltonian. Fine. Good. Let me go to point 2. Right. What we are going to do is to solve a little bit more general problem. In the lecture, we looked at Hamiltonian of free particles and vacuum with eigenstates, with levels which were plane waves, and the delta, which was a constant over the sample. One could think of more sophisticated situation of non-homogeneous structure, some nanostructure which you made from different metals, and then you expect that Hamiltonian is not homogeneous and delta is also not homogeneous. How to describe the situation? Well, we have some single particle levels and both Hamiltonian, which form a basis in single particle space, and both kinetic Hamiltonian and delta superconducting part of the Hamiltonian are arbitrary matrices in this basis. Right. Good. So it kind of generalizes the structure of this Hamiltonian. I need to clear up here a bit. Generalize the structure of this Hamiltonian. So H1 represents kinetic energy. And those are superconducting parts of the effective Hamiltonian. So we consider generalization of this Hamiltonian. This generalization is not to make our life difficult, quite opposite. It's to make our life easier, because instead of summing up our K all the time, we can deal with rather abstract matrices. Fine. So that's what we have. And just for exercise, or perhaps you can just crack it on spot. Let's concentrate on this question. Explain why one can assume that the matrix delta NM here is anti-symmetric. Good. Who can answer this question? Because we are dealing with electrons, okay, it's a little bit indirect manner to answer the question. We are dealing with electrons, which are fermions. Fermions, right. You're getting to the point. So those are fermion operators, and they satisfy anti-commutation relations. So this thing is just minus CM CN. Yeah, it's a bit clumsy minus sign. Let's make it more pronounced. Good. That's why if there's a delta, if matrix delta has symmetric part, it won't just contribute to the sum because of commutation relations between the operators. So we conclude that it is a significant part of this matrix is anti-symmetric. It is very similar to first question of homework one. All right. The rules exchange indices under the sum and derive some symmetry relations for matrices involved. Good. We got that delta is anti-symmetric, and we bring this Hamiltonian to some, well, they call it conventional form. Where relational operators come in pairs. And the way to achieve this is something which looks completely redundant. And it is redundant. We double the set of operators we deal with. So we introduce double sets of operators, ascribing an operator to an operator an index alpha, which can take two values, E and H. E stands for electrons and H for holes, but yeah, it's a bit, it's not self-explaining, but well, we will see. We will see why it is E and H. Right. So this is the set of operators. For electrons, these are creation operators. And for holes, those are annihilation operators. So why it is a doubling of the set? If I consider, for instance, the conjugated, what I have here, N, E. This is C conjugated N, but we can use this. This is actually D N H. So each operator in the set, it comes twice. It's a doubling of the set. So what is the use of it? The use is that we can rewrite it. We can rewrite the Hamiltonian in a question as this in this matrix form. Okay, here we have this matrix surrounded by vectors. That's a vector D, which has two blocks. Let me draw blocks. The electron, the hole, and here I have the conjugated electrons, the conjugate the hole, the conjugated holes. All right, and these two vectors, which are separated in blocks, surround this funny matrix, Bogoliubov-Dijon matrix. Right. And we want to show that these two are equivalent. Again, if we go backwards, if we start with the answer, and we can easily reproduce this form, something which we know. All right, let me do it as follows. Let me do it element by element. So, for instance, let me concentrate on contribution of this guy. Right, what I get by multiplication of So that comes with the H, and it is right. Needs to yeah, non-diagonal. But that is if we now recall this formula, this is nothing but let us see C. So this is what we get. Not to forget this sign. Right. Let us compare with what we got. Yeah. We have reproduced this term. Everything is fine. We need to check H. And here's a little trick. So let us see. I deal with this term. So it has electron operators. So I concentrate on this term. It is 1/2 the so I can immediately write it in terms of C operators, and I reproduce the expression which I have. Very common expression, but only with 1/2. So I reproduced half of it. Where is another half? What was the question? Let us see. What do these reversed operator heads mean? Okay. These reversed operator heads are called checks. And this is to distinguish an operator, creation annihilation operators, combination of those from a matrix. So the matrix corresponds to D and M. To distinguish matrices in the basis and operators in Fock space. Good. So we reproduced only half of this, it seems. Yes, I need to separate a bit. And what do we do next? We look at this particular combination. Again, reversed. Reversed. Ooh, it's a bit more complex. It is 1/2 minus H T, and here I have holes. So I write C is here, and C conjugated here. Let me restore indices. Good. So now I want to use, yeah, now these operators are in the wrong order. C conjugated is on the right. I want to change the order. I use commutation rules, anti-commutation rules, And if n is not the same as m, what do I have? I have minus, which compensate this minus, Okay, now those are in correct order. No, sorry, n, m. This is important. But if n equals m, I have also in commutation relations there's one. So in addition to that, and it was in the formulation of the problem, I have for n equals m1 here, so sum over n minus 1/2 diagonal elements. This is the answer for E naught, which has been introduced in the formulation. Let me look at the formulation again. That E naught. Good. It's just a constant, so it doesn't rely on commutational properties of the Hamiltonian. Commutates with everything. That's why it's not relevant for any Hamiltonian. Just constant energy shift. Right. We still have to deal with this, but anyway, what we need to do is to understand that transposition and change of indices, exchange of indices is just the same. So in fact, this delivers the missing half of this H term. So this is C M H M N. I transpose indices CM. Fine. I think we're done. Right, so let us have 7 minutes break at this point. You like the breaks? Frankly, me too. Let me stop the recording. Recording. I see some questions. I'm still a bit confused about the derivative with respect to delta in a part A. If we have a complex function of z, z conjugated, the complex derivative with respect to z does not exist. How can we now just take the partial derivative with respect to delta, while delta is a complex variable? How that is consistent? Serchan, I don't understand the statement that the complex derivative with respect to z does not exist. If you mean that this function is not analytical, this is fine. But it doesn't mean that you cannot take its derivative with respect to z. I'm not sure whether it's or shouldn't we view this as a real derivative, but more as a variation of delta? and minimizing it with respect to variation. It's important to know that derivatives are variations. How can I do this? Okay, let me first share the screen. I was going to do this, and let me answer the question. Yeah, derivative. So the function of z conjugated is z conjugated. It's a variation. Is z conjugated z plus delta z conjugated plus delta z right. So I conclude looking at the first order derivative that the f dz is z conjugated, and df dz conjugated is z. That's fine. Right. I guess what was your answer was about what's about analytical functions, and those are functions which depends on z only with no dependence on that conjugated. Right, then it's analytical. It can be represented as a Taylor expansion. Okay, you know all this. Good. I need to remove this. Very good. Eraser. Good. Let's get to the problem in hand. Now we want to make the use of this double matrix, calligraphic H. And we want to present it in terms of operators gamma, which will become quasi-particle operators soon. Quasi-particle operators. And we want to implement eigenvalue, the representation of the matrix in terms of eigenvalues and eigenfunctions. So this matrix H works on eigenfunction F, and F depends on N and also on has electron hole components, right? And it gives F has index K, and it gives energy corresponding to K, right? Eigenvector. So what we can do about this with the aid of this relation, we can reproduce yeah, and we are talking about any matrix, any eigenvalues and eigenvectors in any basis. Yeah, it can be seen. Yeah, let me write it as Perhaps it looks better in bra and cat notations. Have a difficulty to write K here. Okay. Good. So it's a representation of any matrix known in linear algebra. Yeah, if you remember this, the rest is trivial. Because for the total operator, we just need to surround this with vector delta. And we call this gamma. Here we are. We have solved the problem. So now we know what gamma are. This is a brain. So I want to rewrite this in components. So it will be a bit lengthy. Gamma with index k. It involves eigenfunction. Okay, this is brass, as I have to write complex conjugation. Let us see. It has index k, and it depends on n and alpha. Have summation over n alpha. And here I have this. I have this here. Now this alpha can be electron and hole, so that I can rewrite it as follows. Gamma k is supposed to be annihilation operator of a quasi-particle. So first I write terms with holes, with electrons. Instead of alpha, I just put electron. And I will have annihilation annihilation operators for electrons. But I have also whole term. I have whole term. Summation over n. And that is conjugated. Good. So this quasi-particle operator, as promised, as we discussed in the lecture, is a superposition, linear superposition transformation of this annihilation creation operator. So it doesn't correspond to any definite torch. It is a superposition of electrons and holes. That's why we use this indices electron hole. Good. To add to this transformation from gammas to from these to gammas, we can also easily revert it because this transformation is unitary. So any transformations generated by this expansion, so this presentation of the matrices are eventually unitary. Yes, I will look at your question, because is A, H, or N under the sum? It is N over the sum. So yeah, sorry for my bad writing. This is supposed to be N. So we initially sum over N and index alpha, which takes two values, summation over N remains. And I put two terms with electrons and holes separately to illustrate that they correspond to operators of different kinds. Good, we have done this point. And now we, where did index K go? It belongs to this, I just keep it in this expression. So those are functions of N and H. Let me write it without indices, and it has index K. All right. Fine. Let me go to next problem. We still have to deal with this doubling. And this doubling is why do we have to deal with this? Initial operator set of these was doubly defined. So we find the same operators in this set. And now we want to remove this. And then the set of gammas which we have also had this leg. Now we want to remove this doubling. And in order to do this, we find this interesting special property of the matrix. So for each eigenstate with eigenvalue E, there is an eigenstate with opposite energy, which means that eigenvalues in the spectrum of this Hamiltonian always come in mirror pairs. So if there's a level at this position, there's necessary a level at opposite position counted from 0. Right. Moreover, there is a special, it is known how eigenfunctions of these states are related to each other. So there is a combination of transposition and complex conjugation. Right, so basically we need to do two things, prove this property, and then derive the relation for operators gamma at opposite energies. All right, so how to deal with that? We just can be done in different ways. So let me recall the definition of matrix. So let's see how much time do I have. Not much. Um, good. I just wonder how much time would I like to spend on this. One wants to check if this eigenvector corresponds to opposite energy. Let's see how can I do it fast. Is it pch of Cn in the first vector next to the matrix? Okay. Each block here is a matrix in the basis of n. So this vector also a vector in the basis of n. It has two blocks, electron hole, electron block, and hole block. This is electron block of the matrix. This is hole block of the electron. This is electron hole, and so on. Right. So index n works within the block. So let me just conjugate it first. But see, I conjugate and that gets transposed. And if I conjugate this is Hermitian conjugation. So yeah, it will be Hermitian conjugation. But since H is self-conjugated, I just don't write anything here. So I conjugate this. I conjugate this conjugation. I added a certain k, I skip k. Hold. This is real. So it stays. I need to do what? I need to transpose indices. I can do this by multiplying everything with matrix, which does it. This matrix is a unity matrix. I have to do it here and here because I also have to transpose electrons and holes here. So what I finally want to compute I don't want to run it now step by step. It's just a matrix multiplication in the blocks. What it finally turns out to be the same matrix, but with minus sign. All right, that proves the hypothesis. What I have to use, and this is important, that matrix delta is anti-symmetric. So delta transposed is just minus delta. All right, I've done this. Let me understand what do I have to do. Making use of psychoanalytic relations for the eigenfunction of H proves that operators satisfy the canonical commutation relations. Yeah. So this is that part we did already. Max Rus has dealt with this in one of the presentation sessions. Orthogonality relation and basically these transformations are described by orthogonal matrices. The relation between operators gamma k at opposite energies, we just need to look here and replace let us see. I have forgotten delta here. So we need to substitute here opposite eigenvector. So instead of delta instead of this part, we set some k minus k opposite energy and h. And instead of this, we substitute minus k and electron. And now compared with this formula, and it appears to be just conjugation. So at opposite k, they're connected by conjugation. And they obey usual canonical anti-commutation relations. So operators gamma, they represent a set of creation annihilation operators for electrons. Now I can go, there are no questions. I can go to next step. Fine. A good thing to know is that where is this? That we still have 1/2 here. 1/2. And now we understand why this 1/2 is. It's because of doubling. Since we have doubled the set of operators, we have to keep this 1/2. Now I'm going to cancel this 1/2. So I want to come to this formula, starting the expansion, I write it as sum of K first at gamma K E K gamma 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 1/2, not to forget. The summation goes over any K. So let me rewrite it as follows. Basically, I separate K onto groups, those which have positive energy. And let me just, for simplicity, to write it like this. K with positive energy. Okay. And here I write it like this. Where energy is positive. I want to now add the same K at opposite energy. I want to add K at opposite energy. Energy has switched to minus EK. Why do I write psi? That's not good. Gamma minus K. Gamma minus K. All right. So now I need to recall that gamma K is gamma minus K is gamma K. That we have derived in the previous point. Fine, I write it as gamma K, gamma dagger K. Fine. So now I use only operators from a half of the set. I removed the doubling. Let me just get it to conventional form. And to this end, I want to exchange these operators. So I replace it. Let me write it like here. A 1 minus gamma good. The first term stays. The second term I will bring here. I will bring it here, and it cancels factor of 1/2. It removes doubling. So we prove that these operators gamma, they really represent quasi-particle excitations. They have positive energies with respect to ground state. Now we want to understand the rest coming from this point. What we find is the energy of the ground state. And what is this? It is minus 1/2 sum over all positive EK. All right, that completes our program. That completes our program. Just a second, let me formulate. We got two things. We have found excitations, the energy of excitations. And simultaneously, you know, twee halen één betalen. Simultaneously, we have obtained the formula for the energy of the ground state in terms of these excitation energies. Those are different things, ground state and excitations. But in this approach, one can show that these are in fact equivalent things. Energy of the ground state can be expressed in terms of energies of all excitations in the system. The question, what about E naught? E naught contributes both to energies of the ground state and energies of excitation. That's why I just throw it away. Both ground state energy and excitation energy are defined up to this E naught. All right, good. So we have accomplished this program. Let us see what else do we have to do about Bogolyubov-Dijon equations. Also, write down so for Hamiltonian separator. Okay, concrete example where n is k and sigma, and compare the results. Right, in principle, it's rather straightforward algebra. There is one point which I have to outline, and it's eventually written here. We've been talking about this matrices. Remember, there was also conjugated term. And if we neglect spin in this direction, and if you put n to k and sigma, it is important that C's here come with opposite spins. So one can see this matrix at each k as let me write spin index separately. There is no delta for same spins. There could be no, because it has to be antisymmetric. So here I have delta for up, down, and here minus delta down, down, up. Good. So in usual superconductor, where spin is conserved, superconductivity always produces the structures known as spin singlets. So Cooper, it corresponds to the fact that Cooper pair comes in the form of spin singlet. You might remember from the story about spin what are spin singlet functions for two electrons. Two electrons with spin 1/2 if they form a state with opposite spin. This is a superposition of their states with opposite spins. Superposition like this. And we find this spin-singlet structure in the definition in the definition of superconducting order. So it's just manifestation of the fact that manifestation, I guess I got a bit tired after all, was a long presentation. This is manifestation of the fact that Cooper pairs have zero spin. They're made of two electrons with opposite spins. They form spin singlets. Fine. Let us see what we can do about the second presentation, because I wanted to do it to do two. Second presentation is rather short. It's mostly about again, it's practice. It's practice, and one wants to take an expression of the energy from the book and compute the energy difference, which is gained by transition to superconducting state. So there was normal metal without superconductor. We have discussed that superconductivity is actually energetically favorable, and if we would like to have counted expression for energy. Good. So we start with this strange formula that we have obtained by diagonalizing energy levels within number box, and that was potential energy, kinetic energy and potential energy. And we want to do the things actually. We want to, guess I missed something in this transparency. Did I put it further on? Oh, no. Okay, I got it. And we have to deal somehow with this coefficient U with interaction. All right. Let us first answer this question. What is the corresponding ground state energy of the non-interacting Fermi gas? That's simple. We need to look at this answer. And we have to set delta to 0. That's basically kills the second term. What happens here? I need to replace by this. So this is 0, or all this bracket is either 0 or 2. Why is it so? Because this is just signum of an, okay, let me write it. Sum over k, epsilon k, 1 minus signum of epsilon k. What does it mean? It means that a 0 at at opposite energies, opposite epsilon and minus 2. At negative energies. Let me plot this function. Okay. Then it's logical. It means if the state is filled, it doesn't contribute. If the state is empty, it doesn't contribute to the energy whatsoever. And for field states, I just sum up the energies. I have no, I don't have questions. Sorry. All right. And now I want to understand what superconductivity gives to me. It gives me this contribution. And there's also delta here. So if I replot this expression, that's what I get. Delta makes this cusp in a little bit smooth fashion. Right. Now I want to compare the energy difference. Good. That gives me a simple idea. What I have to do here, I have to take the difference. So, in fact, I need to compute integral. I need to compute this area. Fine. But there's a problem. This integral has log divergency. Formally, it is infinite. So one can get a little bit desperate at this point, but the point is that there is another term like this, and that has to be taken into account as well. And I have a trick. I have self-consistency question. So this is what we derived, right? And from this expression, from this equation, I can eventually do what? I can express U, which is in this formula. Right, so V delta squared U is minus sign because U is negative 1/2 sum over K D squared K plus delta. Fine. I have to bring it here. Let's see, didn't I forget it? No, I guess it is Oh, sorry, I've forgotten delta squared. So now I want to write everything together. I have to bring this term and replace summation over k by integration, okay, volume in front of it, integration over energy with some density of states. There was a hint that this can be taken by constant. So this expression, after I brought all terms, is not divergent anymore. I can write it as a function of epsilon. I can do the integral. And this is the answer. As you see, it is negative. Delta squared is positive, so the answer is negative. It's proportional to volume. It's energy per unit volume is constant. That's it. That's what we prove. I didn't want to make an integration explicitly. It's a little bit boring. Right. I believe I finish my presentation. My time is down, so I stop recording. How can I do this?